Okay, 56. So we got two charges here. We got 1 microcoulomb, so make sure, micro, 10 to the negative 6. This is negative 2 times 10 to the negative 6. Okay, so this is a negative charge. This is a positive charge. Shh. Hey, are these big dudes or little dudes?
Big dudes.
These are big dudes. Big dudes create the electric field. Little dudes are the ones that go into a field and experience a force, so they get moved around. All right, now A, for point P here, the first question, what is the electric potential due to this guy? So we're just focusing on this guy. What's the electric potential here due to him? Now look, on the quiz, what's the other thing I could ask you? Not electric potential, but electric field. And you should know at this point that electric fields are a lot more difficult to do because they're vector. Electric fields are all about force. Does force have direction? Uh-huh. So it's a vector. So let's just say hypothetically for a moment, just so you're all set for the quiz, what if the question was find the electric field from this guy at that point? The first thing you would do is you'd go, all right, electric fields go out like that. So boom, right there, the electric field is going that way. Okay. How about for this guy? Which way is the electric field for that guy going? It's going that way. Okay. So then what you'd have to do, like if you wanted the total electric field here, it becomes a vector problem, right? Where you got to solve for angles. You got to figure out, well, what's that angle? What's that angle? Figure out your total x. Figure out your total y. The answer would be that hypotenuse. Electric fields are more work. Electric potential, if I ask you to find electric potential, it's easy. It's easy. Oops, I want to add that back there. We're going to need this in a minute. All right, so point P, we want the electric potential from this guy at that point. So for A, all you got to do is go electric potential is KQ over R. That's the equation for electric potential at a distance from a big dude. So this is going to be 9 times 10 to the 9th Newton meter squared over Coulomb squared. Q, make sure you put it in coulombs, 10 to the negative 6 Coulomb. And then R is this distance right here, 0.5 meters. So this gives us positive 18,000 volts, which is joules per Coulomb. All right, now B, same exact thing. So now we want the electric potential for this guy at that point. So you go KQ over R. So that's 9 times 10 to the 9th Newton meter squared over Coulomb squared. Negative 2 times 10 to the negative 6. Guys, in this equation, Q is not absolute valued. If it's negative, you got to plug in negative. And that's not the case in the electric field equation. In the electric field equation, the Q is absolute valued. I promise you, next chapter is more fun. This chapter is very tedious. Okay, so V comes out as negative 36,000 volts. So hey, man, that's A, that's B. Question C, find the total electric potential at point P. So look, if you want the total electric potential at that point, all you got to do is add A and B together. No vector stuff required. No tip to tail, just add them together. So the answer to C is negative 18,000 volts. It's scalar. Okay, now part D is the part that most students need some help with. And I don't like part D. I don't like the wording of it, to be honest with you. What is the work required to move a 3 microcoulomb charge from infinity to point P? So look, sure. The reason I don't like this problem, just to get it out in the open, is it sounds like some outside force is doing the work, In reality, in this problem here, what moves this 3 microcoulomb charge? The electric field itself. It's the same thing. It'd be the same thing as like dropping a brick off a building. As the brick falls, what does the work? Gravity. So yeah, work is being done, but I don't know, here it makes it sound like some outside force has to move this charge, when in reality, this charge is just going to like free float. It's going to be moved by the electric field. Okay, so here's how you set it up. It's all in the setup. Okay, so I'm going to grab this guy. So here's, you got to give yourself a visual. So I got this dude here. Oops. So I picked this picture because it just has an electric field, right? So here's a positive charge. This red arrow represents the electric field. Now, when you do problems like this, you have to have the potential difference. Remember? Knowing, so like at point P, what did we find out about point P? We found out that the electric potential there is negative 18,000 volts. Is that very helpful to know the electric potential at a single point? You can't really do much with that. You're like, all right, great. The electric potential at point P is negative 18,000. When does electric potential become useful? When you have a difference. So look, part D gives us a second point. What's the second point in part D? Infinity. Now what do you have to know about infinity? At infinity, so look at the equation, KQ over R. If R is infinity, like you go super, 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 super far away from the charge, when R is infinity, what happens to V? It goes to 0, right? So dudes, we have 2 points on this electric field here. We got 2 points on the electric field. What are the 2 points on this electric field? We have, the 2 points are negative 18,000, which is this point right here, and then the other one is 0. Which one goes where? So I'm going to put 2 points here on this electric field. Which one would be the 0, and which one is the negative 18,000? What do you know about what happens to electric potential as you move up the electric field? Here's the definition of electric potential. The definition for electric potential is potential energy per charge. Everything is based on a little positive guy. So stick a little positive guy in here. Where would this little positive guy have more potential energy? Up the field or down the field? Up the field. So this point here, let me clean this up. This point here has to be 0 volts. This point is negative 18,000, right? That's how you would set it up. Does that make sense? Why is this one 0? Because what's bigger, 0 or negative 18,000? 0. As you go up the field, volts gets bigger, okay? So these are the 2 points. What's the delta V between them? 18,000. Okay, so look, they're telling us, so what is the work required to move a 3 microcoulomb charge from infinity? So this is kind of weird. Infinity is closer, yeah. Infinity is closer to the charge, the point charge, than point P. But anyway, so here's infinity. So this guy right here is 3 times 10 to the negative 6 coulombs. So look, you put this charge there at infinity, and then let him go, and what's going to happen? He's going to go boo, like that. Now, what's doing work as that positive charge moves down the electric field? What is doing work? What's doing the work on this charge here? The electric field, right? So we're going to go like this. Potential difference is change of potential energy per charge. Change of potential energy is going to be delta V times Q. So our delta V is, so we're going to go final minus initial. So it's negative 18,000 joules per coulomb. The charge being moved is 3 times 10 to the negative 6 coulombs. So we get an answer of, oh, I didn't do it yet. What was it, 5.4? 18,000 times 3.054. So the answer, the change of potential energy is 0.054 joules, and that's the same as the work done. To be honest with you, I would call this positive work. You want to know why? It's work done in the direction of motion. The book says it's negative. I'm not going to lie to you. I don't know why. positive work is work done in the direction of motion. I would say positive. Does the concept make sense?